Let us now dig deeper into estimates of the social cost of carbon. Cody and colleagues describe social cost of carbon, SCC, the discounted value of worldwide damages from the future global climate change associated with an additional ton of current emissions. A slightly more technical definition by Toll links back the social cost of carbon to the Pigouvian tax. Nordhaus describes as major advantages of integrated assessment models that these combine the insights from different disciplines and give internally consistent estimates of the social cost of carbon. The prototypical model is a constraint maximization problem that maximizes consumption path over time subject to a set of constraints that model climate and the economy. So, how are these estimates for the social cost of carbon obtained? Nordhaus describes, here is the basic intuition. The DICE model estimates the path of the economy that optimizes consumption, emissions, and climate change. These calculations take into account the production functions of the economy, the constraints of the carbon cycle, and the rest. One of the auxiliary byproducts of the calculations is an estimate of the impact on optimized consumption of an extra ton of emissions. For example, an extra ton of emissions might lower current consumption by $40, holding consumption in other periods constant, but respecting all constraints. I pause to note the source of this idea. Research of Kantarovich and Koopmans showed that the optimization of a linear programming problem produces both primal variables, here emissions, and dual variables, or shadow prices, here the impact on the objective function of a unit change in emissions. The DICE model produces this shadow price as part of the solution. The shadow price is a mathematical variable associated with carbon emissions in an optimized framework. Later, this was interpreted as the carbon price or carbon tax associated with internalizing the carbon externality. So, in other words, Nordhaus type of integrated assessment models obtain estimates for the social cost of carbon as the shadow price byproducts or dual variables in a constraint optimization problem. These social cost of carbon can be understood as the marginal welfare cost of lost future consumption due to an additional ton of carbon. In Aldi and colleagues, the social cost of carbon are also described as the benefits of emission abatement or emission reductions, which can subsequently be used in cost-benefit analysis. This focus on the marginal impacts on an optimal consumption path may also be considered a weakness of the estimates, as I will illustrate shortly. Aldi and colleagues describe that the review of the Biden administration of social cost of carbon estimates produced the social cost of carbon estimate of $51 per ton. The USA currently uses a 3% discount rate to evaluate climate change relevant projects, showing that this review of the social cost of carbon estimates led the Biden administration to about half the cost as suggested by Nordhaus for a 3% rate, or an order of magnitude lower than what is considered appropriate under low or near zero discount rates. The integrated assessment models used by Nordhaus and others are not without critique. Pindijk, his Coast lecture from 2017, provides a set of such critiques. I read from page 349, putting aside the discount rate problem. Because of the current limitations of climate change science, these models simply make assumptions about climate sensitivity. That is the temperature increase that would result from a doubling of atmospheric carbon dioxide concentration. The figure and table taken from Stern 2008 give some idea of the amount of uncertainty about this climate sensitivity. The figure gives 95% confidence intervals of eventual warming for different carbon dioxide equivalent concentrations, and the table shows a likelihood of exceeding a certain temperature increase for different carbon dioxide equivalent concentrations. The quote from Pindijk continues, "The models likewise make assumptions about the damage function, that is, the relationship between an increase in temperature and GDP. In my reading of the literature, the assumptions on the damage function are most problematic. In an earlier paper from 2013, Pindijk points out sometimes these numbers are justified by referring to the IPCC or related summary studies. For example, Nordhaus 2008 points out that the 2007 IPCC report states that global mean losses could be 1 to 5% GDP for 4 degrees of warming. But where did the IPCC get those numbers? From its own survey of several integrated assessment models. Yes, it is a bit circular. The bottom line here is that the damage functions used in most integrated assessment models are completely made up with no theoretical or empirical foundation. I do not want to give the impression that economists know nothing about the impact of climate change. On the contrary, considerable work has been done on specific aspects of that impact, especially with respect to agriculture. Statistical studies of this sort will surely improve our knowledge of how climate change might affect the economy, or at least some sectors of the economy. But the data used in these studies are limited to relatively short time periods and small fluctuations in temperature and other weather variables. In other words, the damage functions used to estimate the social cost of carbon are either completely arbitrary or need to make considerable out-of-sample predictions. We return to the theme of valuing nature and impacts on ecosystems next week. The quote from Pindijk 2017 continues, and the models, which generally focus on the most likely outcome, tell us nothing about tail risk, that is, the likelihood and possible impact of catastrophic climate outcome, and the key driver of the social cost of carbon. Weitzman once described the social cost of carbon as a battle between the discount factor and the catastrophic damages contained in tail risk, so ignoring tail risk also seems highly problematic. Pindijk also called attention to the problematic feature of focusing on marginal external cost of carbon by pointing out that these marginal external costs are only valuable if we are indeed, as assumed, on some optimal consumption path. In the figure on this slide, we see depicted that if the optimal consumption path is different than found in the model, then the social cost of carbon estimates could be either too high or too low, as shown by the orange and yellow arrows respectively. Finally, Pindijk brings these concerns together in saying, the difficulty with the use of integrated assessment models for policy analysis goes beyond their arbitrary parameter assumptions and ad hoc damage functions. The greater problem is that they create a perception of knowledge and precision that is illusory and can mislead policymakers into thinking that the forecasts generated by the models have some kind of scientific legitimacy. Pindijk instead proposes to use an average social cost of carbon estimate rather than the marginal social cost of carbon that are estimated with these integrated assessment models. He does so with the following reasons. First, this average social cost of carbon is less sensitive to being on the optimal consumption path. Second, unlike the marginal social cost of carbon, the average social cost of carbon remains fixed for a period of time, providing stability for investors. Third, the average social cost of carbon estimates are less sensitive to the discount rate as one discounts the benefits from a larger set of emission reductions or path of reductions, rather than from a single ton change in current emissions. Fourth, Pindijk proposes to calculate this social cost of carbon by eliciting expert opinions, which does not rule out that various experts may wish to use their best integrated assessment model, but Pindijk highlights that this method is at least open about the subjective nature of the estimates, and he proposes a relatively tractable way to estimate it. Here we see the result of Pindijk's exercise of estimating the average social cost of carbon for the coming 50 years, using responses from both economists and climate scientists separately. Which estimates would you tend to trust more?